Hey kiddos, welcome back. We're continuing to talk about the atomic theory. We've taken a little bit of a detour as we are talking about the nature of light and the electromagnetic spectrum. You might recall from last time that we discussed wavelength and frequency and how they relate to the energy of electromagnetic radiation. So as a review, remember if the waves are big distances apart, if it's a big wavelength, remember the frequency is small, that means that poor little girl at the beach, she doesn't get hit very often, and the energy is small. It's an enjoyable day at the beach. However, when those waves are really close together, right, the wavelength is small, right, the waves are close together, that means that frequency is high. So she's being hit and boy, she's having a hard time standing up, and it's a very, very bad day at the beach because the energy that those waves have is quite a bit larger because the frequency is so high. Now, we related that silly analogy to electromagnetic radiation. We said when the wavelength is big, like it is for AM radio waves, that the energy is low, frequency is low. And when the wavelength is small, like it is for FM radio waves, that the frequency is higher and the energy is higher. Let's try that with another example. Let's work with ultraviolet light and visible light. So if we take a look, the wavelength of ultraviolet light is quite a bit smaller than even AM and FM radio waves. It's 10 to the negative 8th meters. That's a really, really small wavelength, kiddos. That's 0.000000001 meters. Visible light, well, it's not much bigger. Visible light is right about here. It's between 10 to the negative 6th and 10 to the negative 7th meters. 10 to the negative 8th. So we're going to call it 10 to the negative 7th meters. So it's a little bit bigger of a wavelength than ultraviolet. So let me ask you a couple of questions. Do you remember which of those would travel faster? Would it be ultraviolet or would it be visible? Okay, good. If you said it was the same speed or same velocity, you are correct. Remember, they all travel at the same speed, which is the speed of light, 3 times 10 to the 8th meters per second. Now, here's the tricky part. Which has the higher frequency? Now, you're thinking, aren't you? The one with the smaller wavelength would, wouldn't it? Isn't 10 to the negative 8th a little bit smaller than 10 to the negative 7th? Yep, so you would say UV would have the higher frequency, and therefore, since its frequency is higher, wouldn't it have the higher energy? Think about this. Why does Mom put sunscreen on you, probably still to this day before you go outside on a sunny day to the swimming pool? Is she concerned about visible light? Or is she concerned about ultraviolet light? Yeah, the frequency and energy of ultraviolet radiation is much higher than visible light. Sunscreen protects you from that higher energy. All right, let's try another one. This time let's work with visible light, and we're going to look at green light. Let's see what else we're going to look at. Violet light and red light. We're going to do the same type of thing. Are you ready? All right, so for green light, what is its wavelength? Now, these numbers here that you can see on this enlarged portion of the visible spectrum are in nanometers. So let's just use those numbers instead of having, something that's on the order of 10 to the negative 7th, 10 to the negative 8th meters. So green light, let's say that would be right about here on our spectrum. It's between 5 and 600. Let's say it's about 525 nanometers. Would you agree? Violet light, let's see, violet light's way over here. Let's go ahead and call that 400 nanometers approximately. Red light, where's red light? It's right over here. Let's just make it easy on ourselves and we'll call that about 700 nanometers. So we have 525, 400, and 700. Now, let's list them in order of increasing frequency. So think about this. How do we put them in order of increasing frequency? Wouldn't it be low frequency to high frequency? Isn't that what increasing means? So which would have the lowest frequency? Which of these waves would hit the little girl the least amount? If you said the one with the biggest wavelength, you're right. So that would be red light. And then green light. And then the one with the smallest wavelength, violet light, would have the highest frequency, wouldn't it? Because the wavelength is the smallest of the three. What about an order of increasing energy? So we're going to go from low energy to high energy, aren't we? So let's put those in order of increasing energy, and which of those would have the lowest energy? Yeah, if you said red, you'd be correct, because the wavelength of red light, of course, is the largest. Doesn't that mean its frequency is the smallest? And if the frequency is small, it means the energy is small. True story? Okay, good. Then what would come next? Green is correct. And violet light would have the highest energy of the visible spectrum, wouldn't it? All right. Hopefully you followed that today and you understand the relationship between frequency and wavelength and energy. Bohr used this knowledge, he used this understanding to develop a model to explain how electrons orbited the nucleus of the atom. And that's what we're going to talk about next time. See you soon, kiddos. Bye-bye.